In southern France, 35 countries have spent more than 2 decades and over $22 billion building a single machine, chasing something that has never once worked anywhere on Earth outside of a laboratory-scale experiment. A donut-shaped chamber ringed by magnets 10,000 tons heavy, designed to heat gas to 150 million degrees, 10 times hotter than the sun's core, designed to hold plasma steady for minutes at a time, rather than the fractions of a second achieved so far. The goal isn't a weapon or a power plant. It's proof that fusing hydrogen atoms can release more energy than it takes to start the one physics threshold that would finally make fusion power a real possibility rather than a permanent promise. This is ITER, the most expensive science experiment ever built, and it won't attempt its first real plasma until the 2030s, a timeline that has already slipped by nearly 2 decades since the project was first proposed.
The energy confinement time is stabilizing right here.
Yes, and the density profile.
Fusion is the reaction that powers every star, including our sun. Atoms colliding with such force, they fuse and release enormous energy. A process so powerful that a single gram of fuel could theoretically outproduce tons of fossil fuel. Unlike fission plants running today, fusion produces no long-lived radioactive waste and carries no meltdown risk. 2 advantages that have kept fusion as the most tempting and most difficult energy source ever attempted. In a modern engineering office, planners studied an illuminated Tokamak cross-section model, the shape scientists have chased for 70 years, a shape chosen specifically because it traps plasma without ever letting it touch a solid wall. Recreating star-like conditions on Earth means holding superheated gas in place with magnetic fields strong enough to keep it from touching anything solid. Magnetic fields powerful enough to have physics almost entirely their own. In a boardroom, officials from dozens of nations reviewed an abstract reactor diagram in 1985. The Soviet Union and the United States first proposed sharing one machine, a rare moment of Cold War cooperation between 2 countries that agreed on almost nothing else. That proposal became ITER, and construction of the actual machine began in France in 2010, eventually growing to include the European Union, China, India, Japan, South Korea, Russia, and the United States. An engineer and a colleague reviewed blueprints on an outdoor table near the research campus, choosing a flattened, forested site near Catarash, a spot chosen partly because the terrain and climate matched the project's exacting engineering needs. The site sat close to an existing French nuclear research center with decades of institutional expertise already in place. Expertise that would prove essential once construction reached its most technically demanding phases. Survey drones mapped the flat construction site. Marker flags tracing out a footprint no fusion project had ever attempted at this scale. Ground that would eventually host more than 60 buildings across the completed campus. The design settled on a tokamak, first developed by Soviet physicists in the 1960s, scaled up to hold a plasma volume of roughly 840 cubic meters, a volume large enough to swallow a small apartment building whole. At sunset, technicians in white cleanroom suits walked toward an assembly hall built to handle components no factory nearby had ever produced before. Equipment so specialized that entire industries had to be built from scratch just to manufacture it. Massive excavation equipment dug a deep, circular pit for the reactor foundation, the first physical step of a 2-decade build, ground that would eventually carry a machine heavier than the Eiffel Tower. A geologist examined seismic monitoring equipment nearby, since the completed machine would weigh hundreds of thousands of tons in an active seismic region, a precaution that shaped nearly every structural decision made from that point forward. Hundreds of cylindrical seismic isolation pads were installed across the foundation floor, minus 493 in total, letting the reactor building float free of ground movement. A system so effective it can absorb the shock of the region's strongest earthquakes. A giant excavator dug into the earth at the pit's edge, dust rising over ground that would soon carry an entire reactor. The first of many excavations that would eventually reshape the entire valley floor. The large circular excavation took shape at the future reactor site, a footprint mapped out months in advance. Precision planning that left almost nothing to be decided once digging actually began. International technicians in clean room suits inspected rebar cages inside the deep excavation, the skeleton beneath a machine meant to outlast decades. Clean room protocols already in force even before the reactor itself existed. Concrete poured into the massive circular foundation slab, layer after layer, building the base for the entire reactor complex. Concrete poured to standards more exacting than almost any other structure on the continent. Seen from above, a large crane looked small beside the reactor foundation pit, an early hint of the scale still to come. A preview of just how much bigger everything on this site was about to get. The French site engineer pointed at foundation blueprints against a reactor cross-section diagram, cross-checking every measurement. So Dupayet, Kauchup, Jida Kagbanve, Dudoy, Nu Oba Jaulu Kakna, Thash Hin. A partially completed foundation rose above the ground, the first visible proof that construction had truly begun. Proof, after years of planning, that a physical machine was finally taking shape. 2 construction zones ran in parallel across the research campus, one for the reactor building and one for support facilities. Thi Kong Song Song Dot Chong Ko Chudich, Larut Nan Manure Nam, Kaiv Amat Tijindo Vorntong Dakeo Dai, Hung Stapaji. At night, floodlights lit the foundation site, a small island of activity in an otherwise dark, forested landscape. Crews working around the clock to keep pace with a project the whole world was watching. Workers signaled a crane operator during a heavy lift, guiding components too large and too precise to move by guesswork. Equipment shipped from halfway around the world, specifically for this one lift. An engineer reviewed geotechnical data on a rugged laptop, confirming the ground could bear a machine of unprecedented weight. XAC Nen, Paya Kotrinswan, Ki Ai Ado, Kote Tinak Sang, Nen Dot, Onan Mai Kosto, Mamai Nazon, Den Te. Rows of soil sample containers lined a geological testing station, part of the extraordinary care required near an active fault region, part of a level of geological scrutiny few construction projects ever require. A surveyor set a total station instrument near the excavation, recording coordinates that would guide millimeter precision assembly years later. A baseline Every later measurement on this site would ultimately be checked against. A convoy of heavy-hauled trucks moved large components toward the site. Machinery arriving from manufacturing partners across the globe. Vehicles arriving on schedules coordinated across dozens of manufacturing partners worldwide. By dusk, long shadows stretched across the finished concrete, a foundation now ready for the steel structure rising above it. The quiet end of Phase 1 on a project that had already taken years just to reach this point. The first steel sections of the reactor building rose from the completed foundation, the visible start of a machine 2 decades in the making. Steel that would eventually support one of the most complex machines humans have ever attempted to build. Technicians welded massive steel wall sectors together, sparks flying as the building's skeleton took shape piece by piece. Welds inspected to standards that left zero tolerance for error anywhere in the structure. A tower crane lifted a massive cylindrical vessel sector into position under floodlights, a maneuver repeated for each of the 9 sectors, each sector manufactured to fit with its neighbors to within a few millimeters. The reactor building's steel frame rose against the sky, cranes surrounding a structure that would soon dwarf the surrounding valley. A structure that would eventually stand taller than a 10-story building. High inside the reactor building, technicians on a suspended platform bolted steel joints together with extraordinary care. Every bolt torqued to an exact specification and logged for future inspection. Aerial shots showed the reactor building's height climbing steadily against the surrounding valley, a landmark rising from open forest, a climb that would take years rather than months to complete. Inside a control cabin, high above the site, a crane operator guided every lift with absolute precision, coordination that left zero margin for a miscommunicated lift. At night, floodlights carved the half-finished reactor building into a dramatic silhouette against the dark valley. Work that rarely paused, even as deadlines quietly slipped further into the future. Week over week, additional sections of the reactor building were completed. Steady proof the world's most complex machine was taking shape. Proof, however slow, that even the most delayed megaproject in modern science was still moving forward. Technicians guided a massive prefabricated vessel sector into place with crane cables, each piece manufactured in Europe or Korea. Components too large to ship any other way than by dedicated heavy transport convoy. Seen from above, the unfinished reactor building looked small against the vast, forested valley. For now, a structure that would eventually dominate the skyline of the entire research valley. Structural engineers checked component alignment with laser levels, tolerances measured in millimeters across structures the size of a building. Tolerances borrowed more from precision manufacturing than from traditional construction. As the building neared full height, the upward camera angle alone conveyed the scale of what was rising from this valley. Scale that made even experienced engineers pause to take it in. A freshly bolted steel joint marked one of the final structural links needed before the building could be called complete. One of thousands of connections that all had to hold under conditions no material had ever faced before. A second major building rose on the opposite side of the campus, part of a site built for far more than just one reactor. A campus built to support not just one experiment, but decades of research beyond it. A heavy lift crane inside the reactor building moved a massive component into the pit below. Logistics as demanding as engineering. Coordination between more contractors than most infrastructure projects ever need. A technician swept a flashlight across a structural support beam, checking welds that would carry the weight of the machine above. One final check before the next phase of assembly could begin.
Rate holding steady at 2 meters per minute.
A giant, cylindrical vacuum vessel sector was lowered into the reactor pit by overhead cranes, 1 of 9, each 14 meters tall and 440 tons. A component manufactured on a different continent and shipped specifically for this one placement. Technicians in clean room suits welded a vacuum vessel seam with extreme precision, joining sectors into a double-walled chamber 19.4 meters across, a seam that had to hold against forces no ordinary industrial vessel would ever encounter. A crane lifted a massive superconducting magnet coil toward the reactor pit, part of a system that would weigh 10,000 tons in total, one piece of a magnet system that, together, would weigh as much as 3 Eiffel Towers. Technicians guided the magnet coil into position, connecting it to the vessel's structure with millimeter-level care. A connection measured and remeasured before crews would sign off on it. Aerial shots showed a partially assembled donut-shaped vessel inside the pit, the Tokamak shape finally becoming visible. A shape scientists had chased on paper for 70 years, finally visible in steel and concrete. Technicians installed cryogenic cooling pipes around a superconducting magnet built from niobium tin and niobium titanium, cooled near absolute zero. Cooling loops that would eventually bring the magnets colder than deep space itself. Frost formed on a cryogenic pipe connected to a magnet housing, a visible sign of temperatures near 4 degrees above absolute zero, a visible reminder of just how extreme the conditions inside this machine would become. Inside a clean assembly hall, massive reactor components sat staged for installation, arriving from all 7 ITER member regions, a logistics operation spanning manufacturing partners on nearly every continent. A giant central solenoid magnet was lowered into the center of the reactor pit, the most powerful magnet ever constructed. A single component representing years of dedicated engineering from its country of origin alone. An engineer inspected a control panel with blinking indicator lights inside a magnet test facility, verifying the system before power-up, verification that had to happen long before any real current would ever flow. Electrical technicians installed high-voltage power supply cables near the reactor building, feeding a system storing 51 gigajoules of magnetic energy, enough stored magnetic energy to be treated with the same caution as an explosive. Thick superconducting cables were connected inside a magnet feeder building, the final link between power and the magnet system. The last link in a chain connecting a power grid to the strongest magnets ever built. In a control room, engineers monitored component assembly on multiple screens, tracking a build spanning components from around the world. Assembly threads arriving from manufacturing partners spread across every ITER member region. At dusk, the reactor building glowed under construction floodlights in the valley. Work continuing well past sunset. Work continuing long after most other construction sites would have gone dark for the night. a technician performed a precision alignment test on an installed vessel sector, checking tolerances that could not be adjusted later. A test that, if failed, could mean disassembling weeks of completed work. At dusk, a completed section of the reactor building caught warm evening light. One more milestone on a decades-long build. Light catching a structure that had taken over a decade to reach this stage. Scaffolding came down from a finished section of the reactor building exterior, revealing the structure underneath, revealing progress that, from the ground, had been mostly hidden for months. An engineer's lit tabletop model showed the completed Tokamak assembly, every magnet and vessel sector finally in place, a model finally matching the real machine rising just outside the office window. At golden hour, the research campus glowed, several buildings visible still under construction across the site, a campus still growing even as its centerpiece neared structural completion.
Adjusting parameters now.
In a control room, engineers monitored assembly progress on multiple screens, coordinating a project built across 35 countries. Coordination spanning time zones, languages, and 35 separate sets of national priorities. A structural stress test sensor was installed on a vessel sector joint, part of verifying millimeter tolerances held under real load. Verification that had to hold under conditions this reactor would face for decades of operation. A test rig slowly moved a mock component through an assembly sequence, rehearsing a lift too critical to risk on the real thing first. A rehearsal considered essential before risking a single irreplaceable component. An engineer reviewed structural test data on a tablet inside the assembly hall office, comparing readings against design limits, numbers that would decide whether years of planning had actually translated into reality. Technicians conducted a precision measurement test near a vessel sector, verifying alignment before the next sector could be added. Checks that on a project this precise could not simply be assumed correct. At night, the mostly completed reactor building glowed in the valley, lights marking a machine still years from first plasma, a machine that, even now, remained years away from ever seeing real plasma. At midday, technicians paused for a break near the assembly hall. Ordinary routine beside the most expensive experiment ever built. A brief pause on a project that had already spanned most of some workers' entire careers. Wide shots compared the massive reactor building against small vehicles parked nearby. The scale impossible to miss. Scale that made the machine's true size difficult to grasp from photographs alone. An engineer stood at the edge of the assembly hall, looking out over a campus built for a machine that won't switch on for years. A campus that had already outlasted several of its own original completion dates. Inside an operations center, monitors displayed magnet and vessel data, part of the extraordinary precision this build demands. Data that would only grow more critical as the reactor approached first operation. A printed engineering report tracked a cost that had risen from an original estimate near 5 billion euros to more than 20 billion euros. A cost overrun that had become one of the most cited numbers in modern science funding debates. At a site meeting, an engineer and colleagues discussed assembly schedules over blueprints. A first plasma date now set for 2034. A date that, like several before it, still carried real uncertainty. Aerial footage from different days showed the same campus view further along each time. Steady progress despite the scale. Proof that scale this large simply takes time, no matter how well funded the effort. A hand adjusted a small-scale model of the Tokamak reactor, planning a machine still mostly hidden inside scaffolding. A scale model finally catching up to a machine still years from completion. The reactor building exterior neared completion, scaffolding still present after more than a decade of construction. Scaffolding that had become such a permanent fixture that workers barely noticed it anymore. In a boardroom, international officials reviewed a large screen showing a rising cost chart, 4 times the original estimate, a chart that had become uncomfortably familiar to everyone in the room. One official's face tightened, reacting to the numbers on screen. The first plasma milestone had slipped from 2016 to 2034, frustration shared by scientists who had spent entire careers waiting for this exact milestone. A drone hovered above the reactor building, capturing inspection footage of joints no ground camera could reach. Routine surveillance that had become standard practice across the entire campus. Technicians conducted a final inspection along the reactor building exterior, checking every panel before certifying it complete. One of countless checks required before any panel could be signed off as finished. A safety inspector checked a cleanroom suit seal before entry. One of countless checks required in this precision-obsessed build. A small but essential precaution in a build defined by precision above almost everything else. By dusk, the completed reactor building glowed, work lights blinking along a structure that took more than a decade to rise. Proof of a decade of work, even with years of testing and assembly still ahead. At dusk, international flags lined the campus entrance. The hardest part of ITER was never really the physics. The physics of fusion has been broadly understood since the 1950s. It was coordinating 35 nations, dozens of manufacturing contractors, and components too large to build anywhere near the final site. A logistical challenge without precedent in the history of scientific collaboration. A scientist spoke firmly at a podium, international flags behind. When ITER's cost was first estimated, it was expected to reach 5 billion euros, a number that, in hindsight, undersold the endeavor by a factor of 4. In a tense negotiation room, officials from different countries sat across the table. Both the cost and timeline turned out to be dramatically wrong. Errors that experts now study as a case study in megaproject planning. A funding agreement document carried an official seal, part of a redesign that switched the reactor's inner wall from beryllium to tungsten, a change driven by lessons learned only after construction was already well underway. A calendar-style chart on a boardroom screen showed the first plasma milestone shifting from 2016 toward 2034, an 18-year slip that transformed ITER into a cautionary tale, even before it produced a single watt. An engineer examined a schedule delay report with a concerned expression. Full deuterium-tritium fusion not expected until 2039. A second milestone that pushes the ultimate payoff even further into the future. Outside a government building, flags stood formal against an overcast sky, representing 35 nations, bound to one shared machine. A coalition that has held together through cost overruns few single-country projects could survive. An official's hand signed a revised project agreement, formalizing a re-baseline after years of slipping targets. Paperwork acknowledging that the original plan needed a fundamental reset, not just a delay. A nearly empty assembly hall sat quiet during a delivery delay. A reminder that components arrive from manufacturing partners worldwide. A pause that, multiplied across dozens of components, added years to the overall schedule. In a small research town near the campus, residents went about daily life beside the most expensive experiment in history. A striking contrast to the geopolitical stakes riding on the machine just up the road. Two officials from different agencies sat in tense conversation. Disagreement over the project's pace evident in their posture. Disagreement rooted in years of shared frustration over shifting targets. At dusk, the reactor building sat quiet, with cranes idle. Critics call ITER a case study in megaproject mismanagement. Criticism that has followed ITER since its very first cost revision. A physicist studied a plasma simulation on a briefing room wall. Supporters countered that no fusion experiment this scale has ever been attempted. A rebuttal that has kept international funding flowing despite the setbacks. A large component convoy arrived at the site at dusk. One more delivery among the thousands needed to finish this machine. A reminder that a project this large moves in components, not milestones. More than 2,000 people now work on site, drawn from over 90 countries, all chasing the same reaction that powers every star. The largest peacetime scientific collaboration ever attempted on a single physical site. ITER was never designed to generate electricity for the grid. It exists purely to prove fusion can sustain itself. Success measured in physics, not kilowatts, at least for this first machine. If it succeeds, it becomes the blueprint for the first generation of commercial fusion power plants. Decades away, but no longer theoretical. Plants that could, in theory, provide power without carbon emissions or long-lived radioactive waste. If it fails or falls further behind, it becomes one of the most expensive lessons in the history of international science. A lesson that could shape how the next generation of mega-science projects gets funded and managed. The sun set behind the reactor building's cranes, a dramatic silhouette forming over a machine that won't switch on for years. Cranes that have already stood through 3 separate revisions of the project's own timeline. Pulling back, the full research campus and valley came into view. A machine 2 decades in the making, finally taking shape. Scaffolding and steel finally resolving into the unmistakable shape of a Tokamak. At night, the valley glowed with distant campus lights, technicians still lowering 440-ton sectors into place with millimeter precision, each one a small, deliberate step toward a reaction that, if it works, changes what's possible. If you want to see whether humanity can actually bottle a piece of the sun, subscribe now. We'll be watching every milestone until first plasma. A story that started with a Cold War handshake and may not finish for another decade.